Bismillahirrahmanirrahim. Assalamu alaikum dear students. We are now starting the third lecture for week number 4 of our course of communication systems. In our last lecture we talked about the mathematical formulation related to amplitude modulation, and we noticed that in amplitude modulation the signal information is represented by variation in the carrier wave. We also noticed that in amplitude modulation the signal is represented at 3 different frequency parts. First is the carrier wave, second is the upper sideband, and third is the lower sideband. The important thing that we discussed in our last lecture was the bandwidth requirement. The AM modulation requires double of the bandwidth as we need for the baseband transmission. In today's discussion we'll be talking about the power consideration in AM, how much power is needed for AM transmission. So the average power of the modulated signal is given by this relationship. St is equal to xc represents the modulated waveform, so xc square is the power, and this bracket here it denotes the average, so we are actually calculating the average power. So average power is actually the power contained within this AM waveform. This is the mathematical form of the AM modulated signal as we discussed in our last lecture, and square is because we are calculating power. So if we calculate average of this entire thing, we will be getting the average power that will be present for that will be required for the AM transmission. So let me simplify this expression. We can notice that AC is a constant number because this represents the amplitude of the carrier wave, which is constant, so I can take it out from this averaging operator. So this AC square is available here. The rest of the term is mentioned. 1 plus mu xt squared is here, and cos square omega ct. 1 plus mu xt square, this can be expanded by simple mathematical relationship of a plus b whole square. So I have expanded this thing, and the second part, you can see that second part is actually we have applied a simple mathematical trigonometric relationship where we can represent cos square omega ct as 1 plus cos 2 omega ct by 2. Again, this 2 is constant, therefore I can take it out, so I would represent it here. And second thing, you should see that there are two terms here. One is this plus 1, and second is this cos 2 omega ct. So we can divide this overall averaging part in two parts, two subcomponents. One is this one, when it is multiplied by 1, so you will get the average of 1 plus 2 mu xt mu square x square t, plus when this part will be multiplied by cos 2 omega ct, so you would get 1 plus 2 mu xt plus cos 2 omega ct. So in order to calculate the averaging, you need to calculate average of these two parts. So let me first discuss the second part, because this has a very good term, which is cos 2 omega ct. Cosine function, we know that cosine functions and sine functions, sinusoidal functions, they have a very interesting property that they are half of the cycle is positive and the remaining half cycle is negative. So whenever we integrate or calculate average over an entire cycle, the result would become 0. For this case, you can see that we have cos 2 omega ct, which is a very high frequency term. So if we have very high frequency, that means we will be averaging over a number of cycles. So no matter, because integration over single cycle becomes equal to 0, therefore integration with a number of cycles would also become 0. So when we get the average of this second part would give an average value of 0 because of the presence of this cosine term, high frequency cosine term. However, there will be some average of first part, so I can ignore this second part and will work on the first one. So the total power, transmitted power in AM, can be written as AC square by 2, 1 plus 2 mu xt plus mu square xt. This is the first term. And because these are three different terms, we can separately calculate the average of each of the term. So this is average of 1, this is average of xt, and this is x square t. In most cases, the message signal also has positive and negative frequencies. So typically, having a signal with positive amplitude and negative amplitude, they occur with the equal probability. So we whenever we calculate this average value of the xt, it also gives a value of 0. So if average value of xt is 0 and this average value of x squared t is, because this average value of x squared t, so is average power in the message signal Sx. So I can write as total transmitted power to be equal to AC square by 2, 1 plus mu square Sx. So you can see that I can this power can be represented as sum of two terms, AC square by 2 plus AC square by 2 mu square Sx. If you focus on this first term, AC is the amplitude of the carrier signal and AC square by 2. We know that the sinusoidal function, whenever you calculate the average value of the sinusoidal function, that comes out to be this value, AC square by 2. So basically this first term is actually the average, representing the average value of that sinusoidal carrier. So I can say that this first term is actually representing PC, which is AC square by 2. Similarly, this part also is equal to the power in the carrier, so I can represent it that by PC mu square Sx. If you recall the discussion related to the sidebands in our last lecture, we discussed that the total power in the AM signal is actually comprised of three subcomponents. One is the carrier PC, and there are two sidebands, upper sideband and lower sidebands. So the total power would be written like this. So if you compare this expression with the previously developed expression here, so this PC is actually representing the carrier power, but this 2SB, this value is actually equal to this PC mu square Sx. So basically the power in sideband is dependent on the modulation index mu. So I can say that the sideband power, which may be upper sideband power or lower sideband power, because both the sidebands, they are symmetrical and they contain same amount of power. So this can be written as AC square by 4 mu square Sx, or we can represent it in terms of PC, that is carrier power, which is half PC mu square Sx. So you can see that the overall power in AM signal is actually comes in three parts. One is the carrier power, and there are two sidebands, upper sideband and lower sideband. So there are two sideband powers. But we know that for modulation we generally try to keep this mu less than 1. So this mu xt is less than 1. That means this mu square Sx, which is representing the lower sideband and upper sideband powers, this is also smaller than 1. In that case, the power in sideband is actually less than half of the power in carrier, or in other words, the sideband power is actually less than 1/4 of transmitted signal. So the overall power in the sideband is significantly smaller than the total transmitted power. It is actually 1/4, so 25% power is in at most we can get 25% power in each of the sidebands. Therefore, we can say that at least 50% power is contained in the carrier. So the carrier contains 50% or more power. In most cases, this power is around 66%, is close to two-thirds. So total transmitted out of total transmitted power, around 66% power resides in the carrier. But we know that the carrier does not contain any information. Information is basically contained in the side bands. So this is one of the major you can say drawback in the AM modulation, that significant amount of the power, it does not contribute in the information transmission, because that 66% power is actually in the carrier only, and we only have remaining around you can say 33% power which resides in the side bands, which actually contribute in information transmission. As a special case, let us take the case of tone modulation. Tone modulation means when the modulating signal is a single tone signal or a single frequency sinusoidal function. And we know that the power in the sinusoidal function is given by a square by 2, so this is am square by 2. But since we are working on the normalized signal, so we are assuming that this maximum amplitude is equal to 1. So I can say that the power in a tone signal is actually 1 by 2. So if we substitute this value Sx is equal to half in the previously developed expression here, which we have shown here, Sx is equal to half, so we would see that the power, again it comprises of three parts. One is the carrier power, and one is the upper sideband power, and third is the lower sideband power. So this will be equal to Pc, thus the upper sideband power and lower sideband powers, they are equal, so they comes out to be mu square by 4 Pc, and similarly this one mu square by 4 Pc, where Pc is the carrier power. So in order to see the effect of mu modulation index in the distribution of power between carrier and the side bands, I have made a simple activity. You can use MATLAB or any other software to calculate this type of expression. So we know this expression, St is equal to is given by this expression. So I want you to calculate the percentage of power in the carrier. Percentage of power in the carrier means this carrier power divided by the total transmission power multiplied by 100. So I want you to calculate this value as a function of mu, and plot that percentage carrier power versus mu. You can plot it on MATLAB or whatever software you feel convenient. And as a numeric value, you may try to find the percentage of power that will be in the carrier if this mu is equal to 1. So as I mentioned, typically the power in the carrier is 50% and more, and you will observe from this student activity, once you plot it, the percentage of power in the message signal. So percentage of power in the carrier, you would see that carrier power will be 50% or more whenever we use the AM modulation. So this is the final expression. If for tone modulation we have this expression, and this is the generalized expression with any specific this one is the generalized expression with any specific signal. In order to conclude the discussion, let us take a simple problem here. The total power content of an AM signal is 1000 watts. So we know that the total power is given as 1000 watt, and we are given the percentage modulation of 100%. So percentage modulation is 100%, that means the modulation index is 1, and we want to find the power in each of the three components, which are carrier power and upper sideband power and lower sideband power. This is the graphical illustration here. The upper sideband and lower sideband, they are present at Fc plus Fa and Fc minus Fa, and the carrier power is at Fc. So carrier power is given by this expression Pc. The sideband powers are both mu square Pc by 4. And we know that the total power is actually sum of these three power components: carrier power, upper sideband power, and lower sideband power. So if we substitute this value, you can see that because we know this total power 1000 watt, so this 1000 watt power can be written equal to Pc plus m square Pc by 2. Or if you substitute this value, because the modulation index is given as 1, if you substitute this thing, you would see that the carrier power comes out to be 666.67 watt. So if carrier power is 666.67 watt, the power in the side bands is equal to 333.33 watt. This sideband power would be actually 333 watt, which is divided into two sidebands, upper sideband and lower sideband. The combined power of these upper sideband and lower sidebands would be equal to 333.33 watt. But we know that the upper sideband and lower sideband powers, they are equal, so we can say that the lower sideband and upper sideband would be this 333 by 2. So each of the sideband would have this power which is equal to 166.66 watt. So three power components are given here. The carrier power would be equal to 666 watt. Upper sideband and lower sideband each will be containing 166.66 watts. Let us take another problem. Actually, this is the reverse of the previous problem, and we want to find the percent modulation of AM wave whose total power is 2500 watt and whose sideband power is 400 watt each. So we are given sideband powers and we want to find the total the modulation index. Again, because this is AM modulation, so total power is actually represented as sum of three different power components. One is the carrier power, one is upper sideband power, and lower sideband power. And in the problem we are given the total power, which is 2500 watt, and we are given the upper sideband and lower sideband power, which is 400 watts each, and from this expression we can simply calculate the carrier power, which comes out to be 1700 watt. But we know that this upper sideband, this is actually related to the carrier power by using this relationship. Upper sideband and lower sideband power, they are equal, and they are mu square by 4 Pc. And if you substitute this value, you can simply calculate this value of modulation index from this relationship. So modulation index comes out to be 0.970. And if you multiply this modulation index in percentage, so multiplying by 100, so we get a 97% modulation index or percentage modulation in this particular case. So this concludes our discussion related to the power in the AM signal. So just to summarize that, the AM signal power actually comprises of three different components: the carrier power, upper sideband power, and lower sideband power. The only problem is that the carrier power, although significant amount of power is placed in the carrier, but that carrier power does not contribute in the information transmission. So the only power which contributes in the information transmission is the upper sideband and lower sideband powers. So if we address this point, that carrier power, because carrier does not contain any information, so carrier power in a sense is wasted, because it is not contributing in any information transmission. So there is a possibility of saving that power by reducing the carrier component from the AM signal. So we can simply remove the unmodulated carrier frequency component from the AM signal, because you recall that AM signal is made of two different parts. One is the carrier signal and second is the product of carrier and message. So if we remove that carrier component, so we can save that carrier power. In that case, the modulated wave can be represented by simple multiplication of the message and the carrier. So this is a variant of amplitude modulation where we do not have the specific carrier component, rather we have the mixed component that comes from the product of the message signal and the carrier signal. This type of modulation scheme is named as double sideband suppressed carrier, because we have suppressed the carrier in the modulation scheme. Sometimes it's written as DSB-SC or DSSC. However, in most cases, this scheme is named as DSB for short. In common usage, whenever we use the term of amplitude modulation, so we generally refer to the modulation scheme where we have double sideband with full carrier. However, when we use the term of DSB, that means we are referring to the double sideband with suppressed carrier, which is presented in this particular expression. So from this discussion, you should realize that DSB is more power efficient as compared to the AM modulation, because all of the power is now used for the information transfer, because all the power is now focused on the two side bands and there is no power which is wasted in carrier. If we look at the frequency domain representation of the same DSB signal, so it appears like this. Again, I have given expression for positive frequency only, ignoring the negative frequency, with the consideration that negative frequency is the exact replica of the what we see at the positive frequency. So you can, if you compare this expression with the previously mentioned expression for AM spectrum, you would see that it has the same form, except that it does not contain the impulse related to the unmodulated carrier. So it does not have that impulse. Other than that, the spectrum is exactly same. So as a whole, the spectrum of DSB signal is exactly same without that carrier impulse. So the transmission bandwidth of the signal is also same, which is 2W. So in other words, DSB signal is DSB signal, they provide benefit in respect to the power utilization or power efficiency, but they are not providing any benefit with respect to bandwidth utilization, because bandwidth requirement remain the same whether you use AM or DSB. But one problem that arises from usage of DSB is can be seen from the time domain representation, because you can see that now we do not have the unmodulated carrier term, so there will be a chance of phase reversal. Whenever the carrier goes to negative side, there will be a phase reversal. So that phase reversal is unavoidable in this DSB modulation. So that means if we want to recover the message signal, we cannot recover the message signal by simply looking at the envelope. If you recall, we discussed in case of AM modulation that envelope represents the message signal, but for DSB signal the envelope does not provide the complete information of the message signal. We also need to have the knowledge of the phase reversals which are occurring because xt is crossing 0. So let me show the diagram how the phase reversal occurs. So whenever the message signal goes to the negative side, in that case you would see a phase reversal occurring in the DSB waveform. So this is the DSB waveform. So that means we need to have the phase information at the receiver side in order to properly recover the original signal. That makes the receiver circuitry more complex as compared to the uh, AM signal. The good thing is that the entire carrier is suppressed, and we do not invest any power onto the carrier. So all the power that is present in the signal is focused on the side bands. So each side band contains half of the power, which is given by this expression, half AC square Sx. So in other words, DSB makes better use of the total average power available from a given transmitter. However, there is a compromise, a trade-off between power and complexity, because DSB conserves power, but at the receiver side the demodulation process becomes complicated because we need to incorporate the phase information as well. So we need a complicated circuitry at the demodulation side, whereas AM requires increased power to transmit, but the detection is very simple because we can detect the AM waveform by simply looking at the envelope of the received waveform. So this makes a trade-off between these use of these two types of schemes, AM and DSB. There is another variant of amplitude modulation which is named as single sideband. We know that by removing the carrier we can save some power, which is around 2/3 of the total power, but that saving of power does not provide any benefit with respect to bandwidth utilization. But one important thing that we should note, that in amplitude modulated waveform there are two sidebands, upper sideband and lower sideband, and both are symmetrical about the carrier frequency. That means the same amount of information is contained in each of the sideband. So whatever information is contained in upper sideband, the same information is contained in the lower sideband. So when we transmit both bands together, that means we are sending that information at two different frequency spectrum. So one possibility to conserve the frequency bandwidth is to suppress one of the sideband. So we suppress one sideband or filter out one sideband and transmit only one sideband. Either we transmit upper sideband or lower sideband, it does not make any difference whether you are transmitting upper sideband or lower sideband, because in both cases the information transmitted is same. So if we transmit the upper sideband, one sideband and the carrier, so we can not only save the power but also we can save the transmission bandwidth, because now we would not be needing the bandwidth to transmit the other sideband. So bandwidth requirement for the single sideband transmission becomes equal to the bandwidth of message signal. BT would be equal to W. So there are certain advantages of using this single sideband modulation scheme, SSB scheme, because first of all the spectrum space is conserved, because we do not need to transmit two sidebands simultaneously. Rather we will be transmitting only one sideband with actually half of the bandwidth that is required to transmit the two sidebands. So if we conserve this spectrum, that means we can transmit more signals over the same frequency range. So instead of transmitting one signal in double sideband, we can transmit two signals by a single sideband. Second advantage is that all the power is now focused in only one sideband. So we do not invest any power in the carrier as well as in one of the sidebands. So all the power is now focused on the one sideband. This makes a signal much stronger, that can go to the relatively greater distances. Since the occupied bandwidth is narrow as compared to the AM, the effect of noise on the signal is also reduced because noise power is also dependent on the bandwidth. So reducing bandwidth also reduces the overall effect of noise as well. The fading effects which occur in the wireless environment, the fading or randomness effects which occur in the wireless environment, they are also relatively reduced because we are working at a relatively smaller bandwidth. So this use of single sideband provides these benefits. However, there are certain disadvantages as well. First of all, the major disadvantage with both DSB and SSB is that they require complicated receiver circuitry, because for demodulation we cannot do the demodulation simply by looking at the envelope. Rather, we have to get the phase information as well, and we need to synchronize the receiver with the transmitter in order to properly demodulate the signal. So that's why in most cases DSB and SSB are not commonly used, because of this requirement of complicated receiver circuitry. Sometimes we use a pilot carrier, which is actually a low power carrier. Sometimes we use this pilot carrier in order to provide the phase recovery information at the receiver side. Another variant of amplitude modulation is named as vestigial sideband or VSB. Vestigial sideband is actually an intermediate scheme between DSB and SSB. In vestigial sideband, we actually transmit one band completely, so one sideband is completely transmitted, and for the second sideband we transmit only a part of that band, sideband. So which is, that part is called vestige of the sideband is transmitted. So in vestigial sideband only a portion of the lower sideband is suppressed, not the entire sideband is suppressed. Actually this kind of scheme is used in TV transmissions generally. The reason we use this scheme is because of the improper filtering. We have previously discussed that we do not have ideal filters in the real world. The real filters, they actually suppress some signal components. So if we try to completely remove that entire sideband, so it also reduces the amplitude of the low frequency components that are present in the TV signal. In order to preserve those low frequency components, we generally use this vestigial sideband technique, where we only suppress part of the sideband. So this scheme provides a compromise between DSB and SSB, in which the bandwidth is much closer to SSB case. However, the implementation is easier than SSB, because we can use relatively simple filters in this case, and they also include do not degrade the performance at the small frequencies as well. The bandwidth of VSB signal is actually approximated by this relationship: Bt is equal to W plus B, where W is the bandwidth of the message signal and beta is actually the vestigial sideband width, which we leave when we transmit the signal, when we filter the signal from that particular sideband. So these are the three variants of amplitude modulation. In double sideband scheme, we suppress the carrier. In single sideband scheme, we suppress the carrier as well as one of the sidebands. In vestigial sideband scheme, we suppress one of the sideband partially, leaving a part of that sideband to be transmitted through the environment. So this concludes the discussion for this lecture here. So I will stop here. Thank you all.